Okay, interference of waves. Now, the basic principle with the interference of waves is called the principle of superposition. So super as in Superman, and position as in place. Okay, superposition, all as one word. The basic idea with superposition is pretty straightforward. Okay, if waves arrive at a place in phase, that means that a crest meets a crest, we'll get constructive interference. Okay, so we're going to arrive in phase. Very important words, which can mean crest to crest, and all these are codes that you can use, little chunks of words you can use in a test. You will get constructive interference, which means you will get a maximum in an interference pattern. Constructive, maximum. Okay, in phase, crest meets crest, constructive interference. So what does this look like as a picture? Well, that is this wave and this wave appearing at the same place. So here we are. That is this wave which arrives as a crest meeting that one arriving as a crest. And the amplitudes add, so I now have a crest that's twice as tall. And I have the troughs add, so I have a trough that is twice as deep, I might say. Okay, so this is the principle of superposition. Now, it's also perfectly possible for waves to arrive in antiphase. And here we'll see destructive interference and a minimum. So antiphase is going to translate to destructive interference, which means, and we have a minimum. So here we have a wave, this one arrives as a crest, it'll be arriving at the same time and place. Let me just hide that other one so it's not going to arrive at the same time and place as this wave, which is actually arriving as a trough. So trough meets crest, sum to 0, and then this crest meets that trough, sum to 0. So the result is no wave, absence of wave, nothing seen or nothing heard. So let's look at how we can make some, how we're going to make some waves. So if two coherent waves arrive at the same place, we can add the displacements to find the amplitude we will measure at that place. So that's what we've just kind of been through. But they have to be coherent waves. So what is coherence? What is coherent? So to be really straightforward, coherent waves have to have the same frequency, the same wavelength, the same velocity, and they have to have what we call a constant phase difference. So what do we mean by that? We mean it's perfectly okay for one wave to be arriving, say, as a crest at, say, at this time, and another wave to be arriving as a trough at this time. So they're in, say, antiphase. But what's going to happen is, because they've got the same wavelength and they've got the same velocity, and as they march on through time, that relationship where this one is in antiphase with that one, so let's just put an axis through the, so I'm suggesting that this crest is meeting that trough, this trough is meeting that crest, this crest must meet a trough, and the relationship has to stay the same over time. So these have got a kind of quite a big phase difference. They're in antiphase, so you can't be more different in phase. But it's very important that the phase difference remains the same. So whatever this phase difference is, it's not a problem. Any phase difference can be tolerated, but it's got to remain the same over time as the waves propagate. And to be honest, if the waves have the same velocity, the same wavelength, and the same frequency, a phase difference cannot really change unless you change the medium through which they travel, which would, of course, change some of these. Okay, so let's move on to actually making some waves and seeing what happens. So one of the easiest ways to make waves is to just make sound waves. And we've done this in class, and you have two speakers, and you make them coherent by having one source of waves that go electronic, AC waves that go into the speakers, and they then push the air backwards and forwards in exactly in phase, or certainly with a constant phase difference. So I'm going to then have two sort of paths of waves that are going to add and subtract, give us constructive, destructive interference. So how are we going to start off doing that? Well, just for the sake of this example, let's say the frequency of the waves is 3,400 hertz. Now, if we use our V equals F lambda, and I've made a little bit of a mess here, but V 340, F 3,400, which means lambda has to be 0.1 meters. Okay, now there we go again, V 340, F 3,400. So the only way this balances if that is a tenth, 0.1 meters. Okay, so how am I going to use that? Well, I'm going to use that by saying, okay, let's start off with a system where I have, what's going to happen? I've got waves meeting at this point A, where waves from source 1 have travelled 1.3 meters and waves from source 2 have travelled 1.3 meters. They both travelled the same distance. So at A, both waves have travelled 10 wavelengths. So let's say we start off with a crest. After 10 wavelengths, we're back on a crest. So the waves that are on the red line, bear in mind we're doing sound waves, so I've just changed colours to kind of help you see what's going on. Okay, but this is all about sound, so there's no wavelength in terms of colour, I'm not interested in that. So the waves on this red path are arriving in as a crest, and the waves from the green path arrive as a crest. We get constructive interference, and this is at the point that we call the central maximum. Okay, in phase, constructive interference. Now, let's look at point B. Now, I cheated and measured this out earlier, and I know that at point B here, I'm going to introduce a new point. I'm going to call this point B. And I don't seem to have the identical pen. Now, this slightly lighter green line is actually 1.5 meters long in my scale diagram. And this line, now this is my point B, which is kind of in a little bit intruding into that diagram. That's my point B. And this is 1.25 meters long. 1.25, let me just go over that. 1.25 meters. So, if our wavelength, remember, lambda, so 1.25 meters is, the red wave has travelled, the red one has travelled 12.5 wavelengths. So it's travelled 12.5 wavelengths, whereas the green one, okay, so maybe I'll just go over that and say red 12.5, and I've written wavelengths, wavelengths, and the green one has travelled 15 wavelengths. Now, this half is very interesting because it would seem the green wave has travelled an extra 2.5 wavelengths. So when the green wave gets to the point to point B, it's going to arrive, because it's travelled a whole number of wavelengths, it will arrive as a crest in much the same way it had done after 10 waves. But this wave, the one that's done 1.25 meters, because it's done the 12.5, it will arrive half a wavelength out of phase, which means that when the two add together, they will sum to 0, and I will have a minimum in. So this is, they arrive in antiphase. So at B, the waves arrive in antiphase phase. And that means that we have destructive interference. Destructive interference, which I'm not going to write in because I've run out of space, and that of course gives us a minimum in our pattern. Now these maxima and minimums are, maxima and minima are really quite important because they allow us to do a huge range of questions. Now you might get a question like this where you're given distances and you say, is A a maximum or is B a maximum, or and you have to work out for yourself. But one thing that we did in detail when we worked through this was to try and drive in the importance of understanding that if you walk along that line between the two speakers, okay, very difficult to show you inside a room this because these sounds hit the wall and reflect back. So if you could take these speakers outside and still power them nicely, you didn't have a lot of wind or other noises, and then you walked along the line, you'd hopefully be able to pick out these maxima and minima for constructive and destructive interference. And what the important thing here is path difference. The reason this diagram is important is that I need you to understand that if a question picks out the second maximum, then you know that if you are at the second maximum, in order to be at the second maximum, then you need to know that this length will be longer than that length, and the difference in the two paths, in order to be at a maximum, must be a whole number of wavelengths. And if we're at the second maximum, we must know the path difference is going to be 2 wavelengths. Okay, and I could do the same thing and take a whole series of points and say, okay, let's have a look here at the first maximum. If we're at the first maximum, then clearly this line is longer than that line, but to be at the first maximum, I would have a path difference of 1 wavelength. I don't like writing a 1 in front of an algebraic symbol, that's making me nervous now. Now, at the central maximum, of course, there is no path difference, and that's the example that we started with A. There's no path difference at the central maximum, so path difference is 0. And then on the other side, the diagram is reflected. So there's no reason why I couldn't do exactly the same thing over here and say I'll get a first maximum where the path difference is 1 times lambda, which I don't like doing, and so second maximum will be 2 times lambda. Now in between these, you have these interesting regions where you've got a half a path difference, half the wavelength path difference, sorry. So let's just pick a different color and let's go for this first minimum. In fact, let's go for the second minimum there. Okay, so looking for this second minimum, this line with the 3, compared to that line, for a second minimum, it must be more than 1 wavelength path difference. It's 1.5 wavelength path difference. So I want to say the path difference there is 3/2 times lambda. For the first minimum, that must be 1/2 times lambda, or 1/2 times lambda. Maybe I should write that as lambda over 2. And again here, it's going to be 1/2 times or lambda. And of course, I'll have a second minimum there, which will be 3/2 times lambda. So it's kind of important that you can decode that. When you're given a question, you need to be able to say, it's the third maximum, so the path difference must be 3 times lambda. It's the 4th maximum, so the path difference is 4 times lambda, and you can use that. Okay, I must have spoken for too long, so I will set you some questions to do in an assignment, and you can get on with some happy path difference using sound. When we've got sound sorted out, we'll step onto light and talk about gratings and diffraction. Okay.